All right. Welcome back, everybody. And I am back. My apologies for my down energy the past few days, but that is in the past. And thank you for the individual who sent me a $2 PayPal donation. I appreciate it. It's good to know that someone cares, right? Not a lot, just a little bit. That's all we need. But we are here today doing some experiments before the blood moon, and we'll be running it for the next 24 hours to see how it goes. And what you're looking at in the container between Bert and Ernie there, it is silver anode, silver cathode, but also titanium anode and cathode, wire wrapped around the silver coins, connected to the positive and negative outside of the reaction there, putting the 5 volts in. But yeah, first time running it with the titanium and the silver together. And it was very interesting. I didn't even have to hook up electricity. As soon as I put each coin in with the titanium wire wrapped around it, instantly started producing hydrogen and bubbling away. And just from it touching and it being exposed to the silver, the two together having that powerful of a differential between the two. But now one being connected to the positive, the other the negative, anode and cathode, electrical input of 5 volts going in, and we will check back on that reaction throughout. And I had to put it into a plastic container, my glass container jar. First time it's ever happened to me. Usually jars can handle the boiling water, but today it did not, and it broke, and that was why there was a late start. Had to mop up and clean up a whole bunch of boiling salt water. Hooray! But, it's for the name of science. And in the name of science, we are going to learn about plasma crystals. Shout out to the Biolumination channel. Great work that she did here with this video. And I'll pause it a couple times throughout to explain the relevance. If I'm sure anyone following this channel and my work will instantly pick up on lots of it. But one aspect, well, there's a couple big aspects, but specifically how it plasma dust. And it goes into my suspicions of his dark materials, the series based off of the movie The Golden Compass. And those dark materials, well, it's this quantum dust. And that I have suspected that these monoatomic elements, this white powdered dust, is essentially that, this quantum material, quantum dust. And well, that connects into so much more. And we will listen to how it ties into plasma, plasma crystals, and plasma dust.
Plasma is often thought of as a chaotic, high energy state of matter, but under the right conditions, it can form structured, self organizing crystals, something that should be possible. Yet, plasma crystals are very real, and they may hold the key to understanding aspects of astrophysics, fusion energy, and beyond. So, what exactly are plasma crystals?
Plasma crystals potentially holding the answer to, let's listen to that again, quantum
Of astrophysics, fusion energy,
fusion.
and beyond.
Oh,
So, what exactly are plasma crystals? In short, they are
apologies.
self organizing structures that form in dusty plasmas. And under the right conditions, these dust grains interact
First question, is she real? I believe so. Talking to her on her channel. Hopefully she comes on and a podcast with us going deeper into all of this. She does great videos. I think she's real. But more importantly, what she was just saying about how the electrostatic properties create these lattices. Okay, so that's exactly what's going on in lots of my electrolysis reactions are these nanocrystal lattice layers forming from the electric input going on and the electric charge within the reactions.
Unlike solid state crystals, which are defined by chemical bonds between atoms, plasma crystals are governed by electromagnetic forces.
Oh, thank you, Quadrant. All right. Was muted there. Thank you for the support. Sky not the limit. And um, what I was saying, the key part of what she just said there, physical crystals like this quartz crystal, they are held together by the physical chemical bonds, whereas these plasma crystals are held together by electromagnetic forces. And we will just replay that little bit to hear it again.
Interact electrostatically, leading to a highly ordered lattice-like structure. Unlike solid state crystals, which are defined by chemical bonds between atoms, plasma crystals are governed by electromagnetic forces. The particles are held together by a delicate balance of repulsive Coulomb forces and weak attraction.
So right there, that is exactly what we see in a lot of my reactions. Although we'll get into examples of it after the video later on. I'll bring up some pictures, but just the crucial point, plasma crystals being held together of electromagnetic forces, not chemical bonds.
In a unique state of matter where order emerges from the dynamic behavior of charged particles. Their study helps us understand self organization in complex systems, the behavior of strongly coupled plasmas.
Boom, again, right there. The self organizational properties of these plasmas and well, what we always see with the monoatomics, the ormus, the GANs materials, how they always do these self organizations from the electromagnetic fields and interactions upon them.
Fundamental phase transitions, and cosmic dust interactions. Plasma crystals have potential applications in fusion research, nanotechnology, and emerging fields that look at self organizing information systems. Stick around to
Oh, exactly what I have been stating for the last, I don't know, 10 years now. My nanotechnology that has to do with plasma fusion, transmutation of elements, LENR, aka cold fusion, as well as technologies of the future regarding self organization.
the end because plasma crystals are far stranger and more important than they first appear. The discovery of plasma crystals is relatively recent, while the existence of dusty plasmas in space had been recognized earlier. The formation of crystalline structures within them was first observed in 1994 by Vladimir Fortov and colleagues during experiments aboard the Mir space station. This confirmed that in low gravity environments, dusty plasma particles could arrange themselves into highly ordered lattice like formations. Since then, plasma crystal research has exploded with laboratory experiments, theoretical models, and microgravity studies on the International Space Station that continue to this day. All of these have helped contribute to our understanding of plasma crystals and more. To understand the science and applications of this marvel, we will explore how plasma crystals form and what conditions allow their existence, the physics that govern their interactions, including wave phenomena and phase transitions, experiments conducted in microgravity. We will then end by taking a look at the practical application.
And a key part of that, phase transitions, and that's part of what I have been doing with the experiments of the electrolysis, forming these monoatomics in the extreme Canadian winter cold, freezing, and some anomalous results that happen with them under the phase transition. Phase state.
From fusion research to self-organization. And I would like you to let me know if we should make an additional video and expand on plasma crystals and take a look at how they...
I told her yes. I was like, please do make a second one. And all right, I have to, we'll get back to that video, but let's pull up a few examples of what I'm talking about. We have self-organization happening in the materials. I've shown lots of examples of the spiraling that happens, the self-organization aspects between the, I guess, plasma state nano single atom materials, aka the monoatomics, and that, sorry, we got lots of pictures to share in regards to this. For instance, here we have more of some of the nanomaterials that I've been making, and this being an example of the aerogel, but that it is also a crystal, clearly seen that it is a crystal as well as it's in this clear gel form. And just more examples of how these materials are crystals. And you can see here this gel, it broke, and that's actually the cleavage of the chunk that is missing off, and then the reflection of the light coming off, shining off of it, even though it is transparent and mostly clear, the cleavage angle that it broke, reflecting light, aka definite crystal. So again, these all are potential plasma crystals. And more examples of the self-organization. Here we have the spiraling as with the exclusion zones. And yes, just very short clips there, but you can see all on its own in a container, self-organizing, self-spinning, like a galaxy, like a solar system, like all motion within the known universe, constantly rotating, spinning, and due to these electromagnetic forces acting upon these materials. All right, back to the video.
To understanding why it is some people say plasma could be conscious or intelligent. Let me know in the comments below. Before diving into plasma crystals, first we need to understand dusty plasmas, a special type of plasma that contains micron-sized dust particles.
Okay, dusty plasma, these little tiny particles of material in plasma, aka monoatomics.
Suspended in an ionized gas. These dust grains interact with the plasma environment by gaining electric charge. Typically, they become negatively charged due to the collection of free electrons within the plasma. This charge alters the plasma dynamics, leading to the formation of self-organizing structure. For a plasma crystal to form, three major criteria must be met. We need the right plasma environment, proper charge balance, and external forces or lack thereof to sustain the crystal. The plasma environment.
Yes, conscious plasma. That is right. And I do suspect so from all of the results that I've seen observing plasma over the years. It does seem to be conscious, even though there is the electromagnetic field interactions governing a lot of the self-organization aspects. I have observed too many times for it to be not a serious phenomenon. What appears to be other conscious structure or organization that happens within the plasma while it is electrically charged.
A crucial role in determining whether a crystal can form. In high pressure plasmas, frequent collision between dust grains and gas molecules disrupt crystal formation. In contrast, low pressure environments, such as vacuum chambers or space, allow the grains to interact primarily through electrostatic forces rather than being scattered by random gas
So
collisions.
again, we have
Additionally,
more documentation and rewriting of physics and the known universe that the majority of interactions of space dust and plasma is actually due to the EM fields and charges and forces upon them, as opposed to these random collisions.
controlled ion flow is essential as the motion of positively charged ions affects the stability of the crystal. If the flows are too strong or too weak, they can disturb the lattice structure, leading to melting or instability. Charge
And I have plenty of examples of exactly that, of the physical metals melting at low temperature even, and just disassembling due to the overcharge of one or the other sides of it.
electrostatic interactions are also critical factors in plasma crystal formation. Each dust grain is negatively charged, resulting in strong Coulomb repulsion between neighboring grains. However, the surrounding plasma ions and electrons create a shielding effect known as Debye screening, and this weakens the electrostatic repulsion over distance. This interaction follows the Yukawa potential. Additionally, ion wake effects contribute to plasma crystal stability. As positively charged ions flow past the dust grains, they create localized regions of excess positive charge behind each grain.
All right, so that right there, that localized areas of positive charge is exactly what is seen in many of my experiments with the exclusion zones and the alternating positive negative areas of water, and how the materials then organize to exactly that and create these charged clusters and these plasma crystals out of dust.
Generate weak attractive forces that help stabilize the crystal lattice, counteracting some of the repulsion from the Coulomb forces. The third requirement is the presence of external forces to sustain the crystal. In laboratory plasma,
again, boom, number 3, to maintain the stability of the plasma crystal, these outside forces. What's that in my reactions? That is the 5-volt anode and cathode electrical charge going in as this outside force acting upon and stabilizing the plasma crystals, the lattice layers of nanomaterials that form by this. Yes, I sometimes do use lye. I mostly just use normal salts and Himalayan salts and stuff, but that is for the purpose of making non-toxic, less reactive, and especially less potential of nuclear decay isotopes forming, as I have used other chemicals, including lye, with heavier metals, and that then you have a much higher ratio of different isotopes of fission happening and breaking down, and that well, I don't want to nuclearly poison myself with radiation and contaminate my living area. So until I get a proper lab and well, more funding and proper safety to do the heavier reactions that are much more dense in the amount of nuclear reactions that come out of the process, and using other also denser and heavier and more reactive electrolytes. Sorry, back to plasma crystals.
the plasma crystal forms near electrodes, or a plasma sheath, which is a localized electric field region. This helps trap dust grains in a stable, levitating layer.
Boom! Local trapped stabilized layer of these nanomaterials. That's exactly what is seen in my experiments. So let's play this again.
A sheath, which is a localized electric field region. This helps trap dust grains in a stable, levitating layer.
A stable, levitating layer. Big time, boom. So many examples of exactly that in all of my electrolysis experiments, showing these monoatomics being captured by what she called a plasma sheath, the area of, I believe, charged plasma area, something like that.
In space environments, dust grains remain freely suspended, allowing for the formation of true 3D plasma crystals. But in laboratory settings, like the International Space Station, which takes advantage of microgravity, dust grains can move freely in all directions, leading to the formation of fully formed 3-dimensional lattice structures.
So in space, she's saying there's the free floating aspects And I postulate, or seem to have demonstrated, in water, it gives you a similar, not complete, but a similar, less gravitational, more buoyant environment for the electrical charge to dictate the buoyancy, as opposed to this gravitational downward pull solely by the density of the matter itself.
Scientists create plasma crystals using vacuum chambers. A typical laboratory setup follows a structured sequence to ensure crystal formation and stability. First, a plasma is generated using a radio frequency or direct current plasma discharge, which ionizes a low pressure gas, often argon. Once the plasma is established, micron sized dust particles such as silicon dioxide, melamine formaldehyde, or polymer microspheres are introduced into the system.
Formaldehyde, no thank you. Don't need to be experimenting with that. But the microspheres of metals, that's something that I've also been able to generate. And shout out to Jeremiah Pop. I've been talking to him. He's recently conducted experiments where he's unequivocally produced the transmutation of aluminum into iron sphericals, and we're going to be having Jeremiah on very soon to do an episode covering this development and more evidence of LENR.
These particles quickly acquire charge from the surrounding plasma and become embedded within the ionized environment. As the dust particles interact, they become levitated within the plasma sheath and
As the dust particles interact, they become levitated in the plasma sheath. That is exactly what the monoatomics that I create are, and what they do in relationship to, I guess, this plasma sheath that forms in the electrolysis reaction reactors.
naturally arrange themselves into an ordered lattice structure. This self organization results in the formation of a stable plasma crystal. Scientists observe and manipulate these structures using lasers, which illuminate the dust grains and allow for direct visualization of particle motion. By adjusting factors such as plasma density, temperature, or ion flow, researchers can control the crystal's behavior, even inducing phase transitions such as melting, resolidification, or the transition into glassy or liquid like states. These controlled laboratory experiments provide crucial
And I have demonstrated all of that in my experiments, specifically everything she's describing.
insights into the fundamental physics of self organizing plasmas, revealing how plasma crystals behave in different conditions and advancing our understanding of complex plasma interactions in space and beyond. Now that we've covered how plasma crystals form, we can explore how they behave once they are established. Plasma crystals are dynamic, evolving systems that support wave propagation, undergo phase transitions, and exhibit emergent order in ways that challenge traditional physics models.
Okay, so, and my apologies for not sharing my camera currently. It says my internet is low. Oh, wait, now that I stopped playing the video, my internet issues are gone. All right, so again, little demonstration of what I'm talking about here. So these would be some plasma crystals. The nanotubes, these self-organized dust particles of pure metal elements forming from the electrical charge going into them. Exactly what she is talking about, and that it's a solid metal that melts into the dust and then able to re-solidify it by adding in the right energy and phase change states of it. And that you can see they self-organize into these structures. And that is dust. They're these literal dust powder of pure metal elements that, when charged, turn into these lattice enacted crystal, plasma crystal structures of self-organization. And back to the strange behavior of plasma crystals.
Studying these behaviors, especially in microgravity, provides new insights into strongly coupled plasmas, astrophysical dust clouds, and self organizing matter. Plasma crystals serve as wave supporting media, similar to how solids support sound waves or how water supports ripples. One of the most well documented wave behaviors in plasma crystals is dust acoustic waves. These propagate.
And absolutely, Negres coils, self-organization, absolutely analogous. Yeah, I totally butchered that. To negative entropy, and that over the last week, there's been a couple articles and thesis published of these new unified theories of physics based off of neg entropy and this self-organization aspect. Right? Very, very fascinating stuff.
Through the lattice in a manner similar to photons in atomic crystals. These are longitudinal waves, meaning dust grains oscillate back and forth along the wave direction.
So that is some experiments I'm needing to do with cymatics and my monoatomic powders and dust, and see and try and get the the scalar wave, the longitudinal wave interacting with these powders, and see if there are specific reactions such as illumination, aka a I what is the word I'm looking for? Where ionized, if it ionizes the particle, ionizes the dust from the cymatic frequency from the longitudinal and the what's the word? The other type of wave, the third wave that I just mentioned. But yes, that if just those sort of waves are able to ionize the dust, aka activating the dust, the monoatomics through cymatics.
Due to the relatively large mass of the dust particles, DAWs propagate more slowly than traditional sound waves, so they are used as a diagnostic tool to study plasma density variations, charge distributions, and lattice stability in real time. Another important wave mode, known as dust lattice waves, propagates through the plasma crystal and resembles phonon vibrations in a solid state lattice. These waves can exist in both longitudinal and along the wave direction. Due to the relatively large mass.
Rewinding here for a minute, just as very crucial information and about how the lattice forms from the wave interaction. Oh, the lunar eclipse is happening now. Fascinating. And where is those waves? Well, that is the next part of why I need more funding to be able to actually further my experiments and add the waves in. And the fact that it is the lunar eclipse right now could add to the aspect of why not seeing too much monoatomic silver forming at the moment, as well. In the past, it was always demonstrated a relationship to a full moon, and in past eclipses that the production rate of the silver has dropped. And I will do a close-up here in a few to see if that is indeed what we have happening today.
Mass of the dust particles, DAWs propagate more slowly than traditional sound waves. To study plasma density variations, charge distributions, and lattice stability in real time. Another important wave mode, known as dust lattice waves, propagates through the plasma crystal and resembles phonon vibrations in a solid state lattice.
Ooh, see, that's why I replayed that. So the dust in that state resembles phonons in a solid state. Like, very complex physics going on.
Dust lattice waves propagates through the plasma crystal and resembles phonon vibrations in a solid state lattice. These waves can exist in both longitudinal and transverse modes, allowing researchers to study interparticle electrostatic interactions, plasma screening effects, and the stability of self-organized plasma structures. Plasma crystals can also undergo phase transitions, shifting between a solid-like and liquid-like state under certain conditions. These transitions can be triggered by increased kinetic energy, external electromagnetic disturbances, or enhanced wave activity, which introduce disorder into the lattice. Unlike traditional melting, where thermal motion disrupts atomic bonds, plasma crystal melting is highly dynamic and often results in a glassy or fluid-like state. This process has been studied both in laboratory and microgravity conditions. When these conditions are removed, external forces restabilize particle motion, meaning plasma crystals can re-solidify spontaneously, showing off just how they can self.
And that has been demonstrated a few times just by putting in a new electrical charge or the right tone, and the crystallization instantly taking form, and that phase transition happening with the minimalist of energy input into the reaction.
Organized. In addition to liquid-like states, plasma crystals can enter a glass state where particles become disordered yet move very slowly. This behavior closely resembles colloidal suspensions and amorphous materials, making it an excellent model for studying non-equilibrium self-organization. These crystals belong to a category of strongly coupled plasmas where electromagnetic interactions dominate over thermal motion. Unlike weakly coupled plasmas, strongly coupled plasmas behave more like soft condensed matter, displaying ordered lattice formations and
Act more like soft condensed matter displaying lattice connections. That is exactly what we see right here, and that they form these lattice structures. It is a solid made out of dust. It is these crystalline lattice layers that form. And here you can see that it literally stops halfway down the jar. Like there's the top of the water right here. That's air. Here's the metal, the zinc anode in, and then the zinc stops here. And then you have half the jar down, creating this lattice plasma crystal and self-organizing and stopping, and then forming more condensed soft matter dust slash powder or mist at the very bottom, but this exclusion zone that it does not form or build into. Specifically, exactly what she is describing and talking about.
Collective particle interactions. One of the most revealing aspects of this crystal is how they respond to microgravity. By removing
So that boundary layer is obviously where the charge changes and where it goes from either the negative to the positive or positive to the negative. That I need to start testing with voltmeters and checking, but it's a charge boundary layer of this self-organization that happens and structures within these reactions.
influence, microgravity experiments create nearly ideal Yukawa systems where electromagnetic interactions fully govern particle behavior. This allows researchers to test fundamental plasma physics theories, including wave propagation, phase transitions, and self organization. These studies have also helped scientists understand the role of ion wake effects in stabilizing plasma crystal lattices, as ion flows influence interparticle attraction and lattice stability. Their ability to exhibit structured order in a high energy plasma environment makes them one of the most fascinating and unusual states of matter. Plasma crystals have practical applications across multiple scientific fields, making them a valuable tool for research and development. Let's begin with astrophysics. Plasma crystals serve as an experimental model for studying charged dust interactions in space. They provide insights into how cosmic dust clouds evolve, interact, and contribute to planetary formation. Their behavior explains how dust particles accumulate into planetesimals, the role of electrostatic forces in planetary rings, and how interstellar dust interacts with magnetic fields in nebula and star forming regions. Understanding these interactions is key to unraveling the structure of the universe at both small and large scales. In fusion energy research, plasma crystals help scientists understand how dust particles behave in high energy plasmas, a crucial factor in nuclear fusion reactors, such.
So these dust particles, aka monoatomic elements, and their crucial role in plasma fusion.
As tokamaks and stellaritors. Dust contamination in these devices can disrupt plasma stability and reduce efficiency. Research on plasma crystals aids in developing methods to control or remove dust, improving plasma purity and confinement to sustain longer, more stable fusion reactions. These crystals also have profound implications for nanotechnology and material sciences. Their natural self organization provides a model for plasma assisted fabrication of nanostructures, inspiring potential breakthroughs in semiconductors, self assembling materials, and advanced electronics. Some researchers propose that plasma's ability to store charged states and propagate waves could be explored for alternative computing architectures and data processing methods. Beyond practical applications, plasma crystals serve as macroscopic system for studying non-equilibrium physics and self-organizing matter. Their behavior mirrors patterns seen in biological systems, complex networks, and strongly correlated quantum systems, making them a valuable tool for exploring emergent order in natural and artificial environments. With continued microgravity studies,
Okay, right there, how she just said they mimic biological systems, and that gets into the aspects of our elements actually alive. Is plasma really conscious? Is it just the lower base level of life and intelligence and consciousness, and how, yeah, they self-organize and act in the same ways? So let's listen to that again.
model for plasma assisted fabrication of nanostructures, inspiring potential breakthroughs in semiconductors, self assembling materials, and advanced electronics. Some researchers propose that plasma's ability to store charged states and propagate waves could be explored for alternative computing architectures and data processing methods. Beyond practical applications, plasma crystals serve as macroscopic system for studying non-equilibrium physics and self-organizing matter.
Non-equilibrium systems. That's another key part. Shout out to Bob Grenier and Michael Perone, Ashton Forbes, and their discussion yesterday. And that is a very major theme of LENR, is the non. Oops.
Some researchers propose that plasma's ability to store charged states and propagate waves could be for alternative computing architectures and data processing methods. Beyond practical applications, plasma crystals serve as macroscopic system for studying non-equilibrium physics and
Non-equilibrium physics. Sorry, having brain farts. My apologies. Um, and how that is a key part and was brought up and discussed several times yesterday with Bob and Michael and Ashton there.
organizing matter. Their behavior, patterns seen in biological systems, complex networks, and strongly correlated quantum systems.
Strongly correlated quantum systems. My apologies. That's a bit of a tongue twister. Try saying that 10 times fast. But that, again, ties back into my suspicions and my thesis of these being quantum matter, that monoatomics are essentially this quantum dust and are this quantum solid state plasma matter. And that would be why they correlate specifically to quantum systems.
Making them a valuable tool for exploring emergent order in natural and artificial environments. With continued microgravity studies, AI driven plasma simulations, and advancements in plasma based applications, the next decade may bring more than we even think is possible. I think plasma crystals are much more than a scientific phenomenon. They are a glimpse into the hidden order within chaos. From the depths of space to the heart of fusion reactors, they reveal patterns that challenge our understanding of matter and energy. Could this be the key to understanding how it is some people think that plasma could be alive or intelligent? Let me know if we should dive further into this in the comments below. Thank you so much for joining me. I hope you found this video useful. Until next nanotechnology, and
And yes, we found that video extremely useful, and please do make another video on it. Bioillumination channel. It well said indeed. And that, yeah, I agree, Negres. Absolutely. It was a great one. And the key parts of what she described here with these plasma crystals, and that they're lattice induced crystals that are held together by EM forces, the electromagnetic forces, not by chemical bonds. So I'll just play that part again one more time here, as it's so crucial.
where order emerges from the dynamic behavior of charged particles. Their study helps us understand self organization in complex systems, the behavior of strongly coupled plasmas, fundamental phase transitions, and cosmic dust interactions. Plasma crystals have potential applications in fusion research, nanotechnology, and emerging fields that look at self organizing information systems. Stick around to the end because plasma crystals are far stranger and more important interact electrostatically, leading to a highly ordered lattice like structure. Unlike solid state crystals, which are defined by chemical bonds between atoms, plasma crystals are governed by electromagnetic forces. The particles are held together by a delicate balance of repulsive Coulomb forces and weak attractive forces. This results in a unique state of matter where order emerges from the dynamic behavior of charged particles. Their study helps us understand self organization in complex systems, the behavior of strongly coupled plasmas, fundamental phase transitions.
All right. So, right there, it understands. Can we control it with brain waves? Essentially, yes. And um, I have actually experienced that myself in the past with a witness, my friend Eamon at the time, where we went into my garage where I had my experiments going at the time, and there was one where it was had been powered by a triple A battery that had run out. It had been the reaction had been dead for several days. It'll usually run for about 3 to 4 days off a fresh battery, and then so it was about a weekend and no reaction for several days. And Eamon looks at me, he's like, and I had the thought simultaneously, like we had this little telekinetic moment of, and Eamon looks at me, he's like, Bernie, can you get it going again with your mind? And I just like stare at this reaction, and all of a sudden it just starts bubbling and just starts going off and started going, and we were just like, whoa. And yeah, that was a solid 10 years ago now. Shout out Eamon. I'm going to have to track him down just to get him on to verify that that actually happened, because it did. And I guess just have to demonstrate it again. And it's everybody can and should practice and work on such things. All right. So let us take a further look at what I am saying now, that this is clearly, these are plasma crystals, and this being the pink red state that Sir Isaac Newton talks about, and it's a very, very reactive. Hey, good to see you, Bree. And shout out to everybody in the chat watching today during this blood moon eclipse. And not sure I got that one. All right, so what we are looking at are crystals. The different dots here, those aren't bubbles. That's actually light reflecting off of the crystal copper there, and that is potentially or essentially plasma crystals that are forming. And here's another great example that it's only copper. Like this is the top half of a triple copper solenoid coil. That's the bottom half. And also here another triple copper solenoid coil, and that they're both on the anode side and they're connected together above, but that below this level here, it oxidizes blue and brown instead of forming this red pink crystalline structure. And here you can see exactly what I'm talking about, and that there's this another boundary, these self established electrical zones, that on the top half of the reaction you're having either the negative or the positive, and then you're having the opposite inverted reaction on the bottom half of the water, which self-organizes into these ionized or charged zones and states, and thus you're having separate electrochemical reactions happening within this same environment, the same chemical environment, where there's no chemical compound difference between the top and the bottom, other than the charge of the particles and of the water and the reaction that's happening, and that self-organization that forms because of the electrical charge differentials or differences between it and how it forms. Thus, exactly what we were just listening to as the definition of plasma crystals, how they form and what they do. And that's exactly what we see right here in front of us. Yeah, AI, it's kind of good though. If AI truly understood everything, it would probably already be taking over. Hopefully, it doesn't decide to go genocidal. Oh, I saw the moon. Awesome. Be back in 2 months. Have to hang out. And sadly, it is really cold in Calgary right now with snow clouds outside. When I checked, guess an hour ago now, because we are an hour into the stream since I was outside. But I would like to try to see if I can see the moon currently. So I will play a quick video while I try to peep the eclipse outside, if it's still going on. Oh, these videos not long enough, but hey, I guess I only need a minute, really. Oh, or there's this, no, not in this file. My apologies, my very slow computer is slowly loading a file of the self-organization neg entropy example of these monoatomics. Here we go. So you can see the two counter-rotating little mini galaxy spirals of quote-unquote dust. The monoatomic, or that's probably di or triatomic isotope with or compound with oxygen or hydrogen attached to the copper there, as it's not the clear white monatomic that you can see in some clouds above at the bottom of the jar there. It's an above layer that there's those white little fluffy clouds, and then the below layer being that denser red, orange, brown material that is rotating there, and that they are also self-separated and self-organizing. The difference between the white monoatomic, so this stuff here, these clouds is what I'm talking about, and they're about a centimeter or an inch from the top of the water, and these clouds below them you can see, and they're about 2 to 3 inches from below the surface layer of this water, and you can see some of the white cloud moving and the galaxy-like spirals spinning there. All right. Well, I guess I kind of let that play and explained what we were looking at, as opposed to going outside trying to find, see if I could see the moon. So let me try to find a better clip of something to play for a few minutes while we go and look for the eclipse. Actually, yeah, good. There's so many philosophical questions regarding AI and humanity. All right, might as well just play a couple more minutes. Oops. Darn it. There we go. Of the plasma crystal video. So we'll just play a little bit more of it while I go see if I can see the eclipse. And I'll be right back.
And cosmic dust interactions. Plasma crystals have potential applications in fusion research, nanotechnology, and emerging fields that look at self-organizing information systems. Stick around to the end because plasma crystals are far stranger and more important than they first appear. The discovery of plasma crystals is relatively recent, while the existence of dusty plasmas in space had been recognized earlier. The formation of crystalline structures within them was first observed in 1994 by Vladimir Fortov and colleagues during experiments aboard the Mir space station. This confirmed that in low-gravity environments, dusty plasma particles could arrange themselves into highly ordered lattice-like formations. Since then, plasma crystal research has exploded with laboratory experiments, theoretical models, and microgravity studies on the International Space Station that continue to this day. All of these have helped contribute to our understanding of plasma crystals and more. To understand the science and applications of this marvel, we will explore how plasma crystals form and what conditions allow their existence, the physics that govern their interactions, including wave phenomena and phase transitions, experiments conducted in microgravity. We will then end by taking a look at the practical applications from fusion research to self-organization. And I would like you to let me know if we should make an additional video and expand on plasma crystals and take a look at how they might be the key to understanding why it is some people say plasma could be conscious or intelligent. Let me know in the comments below. Before diving into plasma crystals, first, we need to understand dusty plasmas, a special type of plasma that contains micron-sized dust particles suspended in an ionized gas. These dust grains interact with the plasma environment by gaining electric charge. Typically, they become negatively charged due to the collection of free electrons within the plasma. This charge alters the plasma dynamics, leading to the formation of a self-organizing structure. For a plasma crystal to form, three major criteria must be met. We need the right plasma environment, proper charge balance, and external forces, or lack thereof, to sustain the crystal. The plasma environment plays a crucial role in determining whether a crystal can form. In high pressure plasmas, frequent collision between dust grains and gas molecules disrupt crystal formation. In contrast, low pressure environments, such as vacuum chambers or space, allow the grains to interact primarily through electrostatic forces rather than being scattered by random gas collisions. Additionally, controlled ion flow is essential as the motion of positively charged ions affects the stability of the crystal. If the flows are too strong or too weak, they can disturb the lattice structure, leading to melting or stability. Charge balance and electrostatic interactions are also critical factors in plasma crystal formation. Each dust grain is negatively charged, resulting in strong Coulomb repulsion between neighboring grains. However, the surrounding plasma ions and electrons create a shielding effect known as Debye screening, and this weakens the electrostatic repulsion over distance. This interaction follows the Yukawa potential. Additionally, ion wake effects contribute to plasma crystal stability. As positively charged ions flow past the dust grains, they create localized regions of excess positive charge behind each grain. This can generate weak attractive forces that help stabilize the crystal lattice, counteracting some of the repulsion from the Coulomb forces. The third requirement is the presence of external forces to sustain the crystal. In laboratory plasmas, the plasma crystal forms near electrodes, or a plasma sheath, which is a localized electric field region. This helps trap dust grains in a stable, levitating layer. In space environments, dust grains remain freely suspended, allowing for the formation of true 3D plasma crystals. But in laboratory setting, the International Space Station, which takes advantage of microgravity, dust grains can move freely in all directions, leading to the formation of fully formed three-dimensional lattice structures. Scientists create plasma crystals using vacuum chambers. A typical laboratory setup follows a structured sequence to ensure crystal formation and stability. First, a plasma is generated using a radiofrequency or direct current plasma discharge, which ionizes a low pressure gas, often argon. Once the plasma is established, micron-sized dust particles such as silicon dioxide, melamine formaldehyde, or polymer microspheres are introduced into the system. These particles quickly acquire charge from the surrounding plasma and become embedded within the ionized environment. As the dust particles interact, they become levitated within the plasma sheath and naturally arrange themselves into a lattice structure. This self-organization results in the formation of a stable plasma crystal. Scientists observe and manipulate these structures using lasers, which illuminate the dust grains and allow for direct visualization of particle motion. By adjusting factors such as plasma density, temperature, or ion flow, researchers can control the crystal's behavior, even inducing phase transitions such as melting, resolidification, or the transition into glassy or liquid-like states. These controlled laboratory experiments provide crucial insights into the fundamental physics of self-organizing plasmas, revealing how plasma crystals behave in different conditions and advancing our understanding of complex plasma interactions in space and beyond. Now that we've covered how plasma crystals form, we can explore how they behave once they are established. Plasma crystals are dynamic, evolving systems that support wave propagation, undergo phase transition.
All right, I'm back. So fascinating right now. Hey, shout out Jeremiah. Jeremiah, I can send you the link if you want to join, my friends. All right, so outside, I could not see the moon due to its snowing and fogginess where I am in Canada, but there was a large area of the sky that was illuminated with a pink-red glow, and it almost seemed like an aurora borealis, but is it the blood moon and the eclipse and the redness? Could be, and that potentially is that causing the reaction to be red and pink today in front of us, as opposed to the pure white and gray that normally forms in a the electrolysis reaction. Usually monoatomic white material forms first, but it seems like it's jumping straight to this pink red state potentially. And yeah, I've seen, usually it's a green aurora around Calgary, but lately over the last year I've seen a lot of the red and the purple. So I don't know. There's a lot of sun activity, but who knows? Anywho, back to what we're looking at here, and that is this forming the red state because of the blood moon. I'm not sure. We'll have to see how it develops and what forms and comes out of this material. In the meantime, as the reaction continues on, we will take a look at another example of the self-organization of this material. You can see it spiraling, spinning there. And now it's just one giant spiral as opposed to the two that were in the prior video that I showed. And this due to the fact that I took out the aluminum copper. Essentially, it was an electrode, but it wasn't connected to anything that had been in there that separated the two that they formed around, and now you can see just one. All right, so Jeremiah, if you're available and able to join quickly, just to give us a little update on your transmutation results that you have gotten, which is absolutely awesome. You don't have to do a full presentation or anything of the sorts right now, but if you're around, here is the link to join, emailing you right now. Hopefully not, no worries, my friend. Okay, send you the link. It is in your email now, I believe. Yes, it should have sent. All right, so here we can see that spiral, self-organization, and let us get another one. No. Aha. So this one, quite fascinating as it's the original preceding to all of the videos, and it is the white monoatomic top cloudy ormus that you can see doing this double spiral action happening. and that there's the aluminum electrode I was speaking of still in there, and thus separating the two, despite it not being connected to anything, just its presence causing the dual spiral as opposed to the single spiral action observed once it's removed. Now, is this the same? Yeah, it's the same video. All right, so you see pretty good there. Does it change videos for us? Yes, it does. Okay, here you go. Very first video recording of the double spiral formation happening. And I had just poured a little bit of water into the jar, which then created this reaction and self-organization of negative entropy from the charge separation in the water, and how it dissipates and self-organizes into these spirals. And so the two we just saw there of the top of the white monoatomic material, and then this video after I had poured more water into it, which disturbed some of the bottom material, then creating the denser Ormus or GANS material spinning in two opposing spirals. Hey, welcome, Jeremiah. Good to have you, brother.
Hey, how you doing tonight, man?
Good, good. Much better. Got my job back, so I am happy. I am employed once more, so life is good, and I don't hate everything anymore. All right. How are you, my friend?
Oh, quite well. I'm really glad to hear that you're doing better, man. I was concerned about you the other day, and I'm glad that it worked out. I'm just stepping outside for a moment to stare into the sky and see if I can crane my neck around enough to actually get a glance at the blood moon here. It's just going past the top of my building, so I have to look at a slightly different angle for the apex. Yeah, it's definitely getting there. Like it's unfortunately going to be probably outside the range of where I can see it from this side of the building. A bit later when it hits its full apogee, but for now it's looking pretty good. So I'm just I'm going to wait a little bit longer.
You are? Can you turn on the camera? Can we share
it? There's nothing really to see. I mean, it's I have to stretch my head past the edge of the patio railing in order to see it, and I don't really want to hold my phone out.
No need to dox yourself live on camera either, I guess, if you're showing building angles and stuff. Don't need to do that.
Yeah, indeed. So there's a lot of reasons why I wouldn't do that, but anyways, now I have things to show indoors, and what's really recently interesting here is that I was doing these sonicator experiments, because we've heard about Ultra or ULTR, Bob Greenyer's pet project with the ultrasonic cleaning baths, and using those to sonicate the heck out of aluminum foil, and having that aluminum foil show yin-yang type of patterns and the signatures of exotic vacuum objects. But the most interesting part isn't the signatures that are left on the foil. I think that's what a lot of people, kind of stopped at when they look at Ultra. They're like, okay, so there's cool, shiny patterns on the foil and geometries, right? But no, the really cool stuff that happens in Ultra is that the aluminum foil turns into iron-rich crenellated nanospheres. And that is a transmutation process where aluminum becomes iron and also produces byproducts of a series of many other elements. So I successfully did that experiment in my ultrasonic bath quite some time ago, but the amount of iron that I got out of it was so utterly tiny and insignificant that like you had to basically let it settle out for an entire day, and then you would have to go back in there with like the tiny little eyedropper sucker and like try to get the itty bitty little bit of grayish powder that was at like the edge of the bottom. If you tapped it enough, you might just be able to get a couple particles out of there enough to see with your naked eye. But I have another machine, and this would be the first time that I've actually really messed around with it. And I think for this, it might be best to pull out a few things here. Let me see if I can grab some stuff ahead of time, and then I'll flip on my camera. But I'll show you this insane machine that I have. Okay,
yes,
so
please.
Y'all have been to a festival or a music show or something with really big speakers, right? I'm sure most people have stood in front of like a bass subwoofer. Okay, so 400 watts is not a lot of power. It's not, a massive amount of power, but 400 watts is definitely significant. Like there's a decent amount of energy in 400 watts of audio, and especially, if you deliver that energy acoustically efficiently, it can be extraordinarily loud. Tube amps have a particular talent at converting electrical energy into mechanical motion very, very well through their conversion stages, because the transformers that are used to impedance match the high voltage side of the tube amp to the low voltage operating electromagnetic voice coil compensate for the little differences that would normally have to be thrashed through semiconductors. So that's why the sound of tube amps is much better and the fidelity is much better, is because it doesn't inject so much clamping noise. But okay, so here we go. I've got my foil and I've got that thing. And I'm going to turn on my camera.
Very nice.
All right.
I'm excited.
Why is my camera not working? Okay.
Difficulties, that's part of the process.
It says, oh, that's why, because I have to do that.
Boom. We got her.
That's much better. Okay, yes. So this is a probe. I'll zoom into the head there. That's the head of a ultrasonic probe capable of delivering 400 watts of acoustic energy, 400 watts of sound. Just imagine how loud that would be.
Wow.
Into a tip the size of my fingerprint. And
so I need one of these, please. Where do I acquire such device?
This one's made by Fisher Scientific. It's called a sonic dismembrator. This is the Model 500, and the dismembrator part here is, this machine was designed to basically, you are taking a small lab beaker, filling it with some biological material like cells of something that you want to test, and this thing will vibrate so hard and so fast that the cell walls will literally be ruptured. It will dismembrate the cells, removing the membrane that protects them and exposing all of their internal goodies, ribosomes and nucleotides and the DNA. So if you wanted to get inside of a cell, this device is designed to basically get you inside of that cell. But it also is really useful for turning large amounts of stuff that are in big pieces or put together into really, really itty bitty tiny amounts of stuff. So what I did is I took a piece of kitchen foil and about maybe a foot long piece of kitchen foil, folded it a bunch of times until I had it in quite a few layers that, it was a square like this big by like that big. And
Nice.
I shoved that into the bottom of a 200 milliliter flask. I filled that flask with distilled water. And then I just simply brought the probe tip right down to the point where it was just about touching the surface. Now, this probe tip moves in and out. It moves up and down like this, like a piston. So that's the direction of motion. So it produces sound waves that shoot out the tip here and go straight downwards and would hit what's ever underneath it, which in this case was the aluminum. The acoustic energy is so intense that it sends a ripple through the lattice structure of the aluminum metal, and the electrons get ripped off. When the electrons get ripped off And keep in mind, this is surrounded by water, so there is all this pressure from the water, so that it just can't, send particles flying away. The water is pushing down on this reaction as it's happening, and the sound wave being produced by the tip of this is pressing against the aluminum. So the aluminum lattice is distorted. The electrons of that lattice get completely torn off, and now the nuclei of the aluminum atoms are exposed to each other, but there's still the acoustic energy being pumped in. And in addition to just the motion of the tip here that's moving up and down, it's also doing something else. It's producing cavitation within the water. Now, the speed of a cavitation bubble and its collapsing field, or the rate of the collapse, the amount of momentum in the sound wave that it will produce takes the low frequency, large displacement sonic action from this probe tip and turns it into incredibly high frequency, ultra fast impulse sonic displacement. And that impulse is so fast that it can slam the now exposed nuclei of the aluminum atoms together and start fusing them into other elements, which ultimately they tend to end up as iron. But the interesting thing is when it does this, when they slam together, they tend to slam together and form these little crenellated spheres. And the spheres can grow over time. So this I did not actually use the probe tip to jam into the aluminum. It looks like that because I allowed the probe tip to just get close enough, and the sound waves created all this crushing and all, this appearance. So that's all done by sound. That was not from physical contact, and that's why the probe tip is, it looks absolutely perfect, and there's no erosion on it. Now, obviously, this whole entire horn, this was used. This is a used piece of equipment. I got it for, less than $1,000, and it cost like $5 or $6 new. So not too bad, but just that amount of energy can literally rip the electrons off of metals. And so now I want to try other stuff. If I know aluminum turns
them together,
right? So if I know aluminum turns into iron, I wonder what bismuth turns into, or what tin, or nickel, or zinc, or copper, or who knows? What do those things turn into? And so now I've got to run this experiment in a various number of iterations and find out.
Absolutely, we do. And did you, by chance, have any of those little iron spheres available, or was that for
but it's going to be okay. So this is going to be an absolutely garbage video, and I'll try to show you. I have not refined the ones out that I just had drop out of suspension tonight during the blood moon. They finally settled down. I know the pH of that stuff is still high because the other problem with the sonicator is it will rip off any oxygens from the aluminum before it starts actually ripping the electrons off the aluminum atoms. And once you rip the oxygens off the aluminum can now start to react. And because normally aluminum would react with the oxygen in the air, it would form aluminum oxide, which is a sort of whitish colored ceramic material. Aluminum oxide is what they use in anodized coatings to harden the surface of aluminum and protect it from the elements. It becomes less reactive because it's already bound to something. But in this case, it's surrounded by water molecules, so it becomes aluminum hydroxide and binds with the water, which is actually a base. And that base is so powerful that the sonicator turns the aluminum foil and the distilled water into aluminum hydroxide, which then starts to eat the rest of the aluminum foil and generate a huge amount of excess heat. So you have to stop it before it gets too high in the pH or before it gets too warm, because both of those things together create a runaway process that has a logarithmic response curve.
Right? Like that's wild, and that it will literally create a runaway process reaction.
Yeah, it's definitely wonky. But okay, so I'm going to show you a tiny little sample, and I don't know how well you'll be able to see this, but I will try. Okay, so inside this little jar, let's see if I can get this to focus. Okay, so inside that little jar, there's some this like grayish dust. Now, it's not like uber magnetic, because I did say they were iron-rich crenellated nanospheres, but that does not mean they're completely made of iron. They're actually made of a number of different elements, but they do have a high percentage of iron, so they are ferromagnetic, not just simply paramagnetic. And if I jiggle this jar around kind of like I'm doing right now with my hand and get those particles agitated so they're free to move, and I place a magnet underneath, you'll be able to see that it will actually pull them in to the line, it'll want to stick right around the edge. So if I just, I have to take this magnet off here, so I'll lift that up. See if I can show this.
Oh, yeah. Oh, just a little lower to the camera. There we go.
It's not a good angle yet. I'm just going to shake it and agitate it for a little bit, and then I'm going to take the magnet away. Okay, so I took the magnet away, and you can see right at the edge where the magnet was, it pulled them all to that spot. And so if I put this closer to the edge, and I did the same thing, now they're all going to be near the edge when I take it away. I'll just wait for that to settle a second. Yeah, now you can see they're pulled to the edge.
Yes, sir.
So it's a bit weird because they're still suspended in water, but that's a tiny amount. Now I have 2 other jars, and I'll grab those real quick. And these are from my most recent experiment where the piece of foil that I was showing earlier, those spheres that you're looking at were not from that experiment. They were from the one previous to that experiment.
Nice.
So the lighting is not as good here, but we'll see if we can see it.
Oh, yeah.
So in the bottom, there's actually quite a bit of aluminum fine nanoparticles, but you see all that grayish, really dark black stuff. That's the iron granulated spheres. And I have to separate them out from the aluminum still, but that will be a process that I can only do once I change the pH. The reason that this solution is foggy right now, looks white, is because the even though I had drained off all the fluid from the top of this stuff that was left at the bottom initially, it still was reacting and the EVOs were doing work. So literally after the reaction was shut off for the next several days, the EVOs were still coming out, breaking off the metal and going from the dark mode to the bright mode where they actually react, and they were producing even more aluminum hydroxide by microcavitating the rest of the material in there. So this was filled with huge chunks of aluminum before. It's all dissolved, and now it's this white murky powder in suspension. And this is the drain off stuff that was totally dark gray for days, and tonight during the blood moon it went clear finally, and it dropped off in suspension more of the ultra fine nano granulated spheres, and they are sitting at the bottom and you can see them. So when I separate these from the aluminum, I should have a decent little pile that I can send Bob Grenier in a small vial, and I will label them with the date, and I have the video footage of the setup for the experiment, and then he can scan them with SEM and determine what's exactly in them. But the thing is, the process that I use to generate these things and do this transmutation is a process that has never been done so far as I've seen yet, because I don't think anybody just had a 400 watt sonic dismembrator sitting around to play with. Like, a lot of people had ultrasonic baths, but they are not even close to the retarded amounts of energy concentrated at that probe head.
I get you on that. I'm a little bit jealous. We're going to have to talk afterwards of some experiments that I'm going to require you to run for me.
Oh, man, I've been, I also mentioned, I suppose, this other thing that I've been using it for. I didn't pull it out to do ultra. It's just once I had it out, I had already done ultra in a sonic bath, and I was like, okay, well, I got this for another project. I got it to make a special type of metamaterial for an anti-gravity experiment, or I should say an anti-gravity device that is a solid state, no moving parts device, and operates by similar principles to the Graviflyer, but doesn't have any spinning magnets or that kind of goofy stuff. So, anyways, to make the material, I needed to completely micronize a material called chitin, which is usually found in the form of chitosan, and it's derived. Chitin is derived from shellfish. Stuff. Yeah, shellfish and bugs like shrimp, crabs, lobster is mostly what you'll find like commercial chitin sources. They're being sold as chitosan or in that form for. But the chunks, the powders that you get, they're fairly large pieces, and in order to get them to form a very good hydrogel and start to relink protein chains using acetic acid, you have to break them down to the tiniest pieces possible. And in order to do that, I needed the power of the sonic dismembrator to really bust them into extremely nanoscopic sized particles so that they would be able to form a new hydrogel matrix and trap the specific material dopants into that matrix that I needed to interact with the scalar stacked electromagnetic field.
I know exactly what you are doing with that, and that's super cool.
It's going to be a heck of a thing too, because I finally understand how to do it. It took my brain several years to understand the concepts that my mentor taught me, and now that he's not around anymore, I'm starting to talk about what these things were and what he taught me. And this kind of stuff is it. He showed me how to build these, or well, not showed me in person, but described with reasonably high technical detail how to construct these gravitational panels. And
gravitational panels, exactly what I suspected with that material. And it goes back to, what was the Russian Soviet Gravenko that originally
Grebennikov, yeah. Grebennikov discovered that the chitin in a certain type of beetle happened to have the right shaped geometry. Okay, so chitin alone does not have magical, mystical properties. Okay, well, technically it does. Chitin actually is an incredible detoxer if it's properly deacetylated. So, I'm sure I said that word wrong, but it has to go through a process in order to make it useful to a human and not toxic. Otherwise, it can cause other problems. But if it's properly processed, chitin can help you lose a huge amount of weight safely in a healthy way really quickly, because chitosan will go into your body and it will grab hold of, like, each little chitosan particle will surround itself with a layer of fat that'll take out of the body. Like, usually the body has all kinds of fats that are kind of useless to it, and it keeps them around as like an absolute last resort because they're slow to break down, and they would allow you to like fast for weeks if you had them, because they break down so slowly, but you wouldn't be operating at any kind of capacity. So they really don't help us. And a lot of people store around these fats and walk around with these extra fats attached to them. And chitosan will help strip that stuff out of your body if it's not doing any good for you. And it'll leave the muscle tissues enhanced because it also acts as like a little delivery truck for all the phytonutrients that you're consuming. So if you combine it with things like high density multivitamin, or good supplementation of various micronutrients and other minerals and elements that you should be consuming if you're not getting them in your food already, or if you just simply take it in conjunction with meals, then that kind of thing, like it can help your body get that stuff into the bloodstream in a more efficient manner.
But besides, none of this is health advice.
Yeah, it's not health advice. This is just if you go on Wikipedia and you read about the kind of uses that it has, or you go look up like on WebMD, this is the kind of thing that you're going to see it being described for. It'll also warn you, do not over ingest it. You have to actually know what you're doing. You have to have like a medically prescribed dose, and you should see a doctor first, according to all these sites, just to like check out if you're even, if your body is healthy enough to even handle this stuff. So it's not the kind of thing that you should just go, oh, I'm just going to go get that on Amazon, right? And then just start experimenting on myself. Do not do that, because you can really mess yourself up, or find yourself in the bathroom for half a day or something that you just wish you had never done. So anyways, chitin on its own does not have any kind of superior properties. But what Grebennikov found out is that there is this something in nature that causes fields to act weirdly. And it happens when you have something made of a certain shape. This something could be wood fiber, cellulose, or it could be chitin, like in insects, or it could be a variety of other fibers. You could make it out of literally fiberglass. If you wanted to, you could make it out of bamboo. You can Just about anything that has a fibrous structure or anything. Technically, you can make it out of carbon nanotubes, and carbon nanotubes actually utilize this. Is one of the reasons why you have insanely high electron drift velocities over the surface of carbon nanotubes, and why the electrons don't actually flow through the nanotubes or jump atom to atom, but they flow as an evanescent wave across the surface, is because of that geometry. They interact very differently with the external space. And Grebennikov found that if you assemble a left-handed molecule, chitin, in combination with a certain geometry, which the beetle naturally had, and then you stimulated it with an electric charge and vibrated it mechanically and displaced it within that electric charge, that it would spontaneously generate its own magnetic field at the atomic scale. And that magnetic field plus the charge end up having a compound effect that puts a huge amount of energy into the localized stress energy momentum tensor and starts to produce intensified electromagnetic radiation that can operate into the terahertz spectrum. And with all that said, basically he found out that if he shakes beetle wings really hard while they're electrostatically charged, and he has a source of ions, which in his case he used the carbon content of coal or a wood ash that was burned, and then mixed it with some kind of binder into some kind of plant fiber, and coated the inside of the bottom of that as like a negative ion source hooked up to a high voltage pulsed DC power supply. And it was those two things together, the high voltage ion source and then these little wings flapping with their geometric structures under that electric field, that was allowing him to fly around. Unfortunately, Grebennikov, according to legend anyways, or folklore, developed foot cancer as an exposure to what he called lepton radiation.
Really?
Really?
Heard that aspect.
Yeah, and so that's what lepton radiation, which is, it didn't really have a name at his time, so why not call it something interesting? But, this is what Bob Greenyer talks about with strange radiation, where it's a quite damaging type of thing that has a signature of these extremely high energetic self-wrapped electromagnetic fields. It's sort of like the Ouroboros of the electromagnetic world. If you close a field in on itself, then it's somewhat self-sustaining, like a phantom.
Self-sustaining, self-generated magnetic field on the atomic level.
It's a weird thing, man. It's a whole weird thing.
Oh yeah.
I'm sure like most of the stuff that I just said is not going to really serve anybody any kind of purpose or function.
No.
Probably sounds mostly like word salad, but I suppose the people that know about chirality and understand things like benzene ring aromatic reactions and that kind of thing, and has looked at Ron Kita's work, might be familiar with these concepts and start to see why things like chitin with a left-handed spin molecule and carbon plus an electromagnetic field and an electric field can produce weird effects. I do have a paper that I'm working on.
Nice.
Which will help clarify these ideas in a much more eloquent way with less unnecessary words, since I'm kind of producing this description on the fly right now.
Hey, I like it. It's real science, and it's how we manifest our understanding and make sense of it, right?
As best we can.
Exactly. So I've been bringing up a few of these different charts and periodic tables in relation to how you're talking about if aluminum makes iron mostly, what bismuth most likely would do. And when looking at the relationship from the Walter Russell main periodic table, here we can see aluminum is on the 6th octave and it's one down from the middle, and then you got iron, which is on the 7th octave and also is one up from the middle, being cobalt there. So going down to bismuth on the 9th octave being on the outer side there, 3 from center, then you're either going to get actinium or albertin if it does the same up one.
Well, seeing as the rarity of those things, if it did actually upconvert in that fashion, then
right?
if it actually did, like, nobody is going to say, well, that's strange, this must just be contamination of these ultra rare metals in the bismuth that would never occur otherwise.
Right, so now you're gonna have to do it and see if you can produce some albertin for your Albertan friend BurnEye here, right? So
Yeah, I don't think I've ever even said actinium out loud for any reason. I don't think I've ever had a need to.
Right, or some actinium.
It is a cool name to learn, though.
Hey, we'll start producing it, and we'll have all the reason in the world to keep saying it.
Yeah, then we can, get into the whole territory of, I wonder what I can screw with next.
Oh, yes. Gotta love the mad scientist reality when you find a glitch in the matrix. So I believe this was also a Walter Russell diagram, and it's very similar to the Scenario Arrow Club diagrams.
That is interesting. Where did this come from?
These are all Walter Russell diagrams.
Huh. Did he have a label on that one of what he was trying to describe with it?
I don't see it saved. I will have to look into it and find the original for you for it.
Yeah, I wonder what he was trying to represent with that.
There's so many.
Yeah, one thing no one can take away from the man is that his drawings were absolutely gorgeous.
Right? So before their time. And it's like he's the original theory of everything. Connecting sound, light, atoms, motion, energy, spin, octaves, charges, density. Oh, plutonium. So he called it something else before they were actually discovered or invented, I guess. Named.
Yeah, I think when I have to print out some of Walter Russell's elemental charts.
Oh, yes.
Just to kind of determine like which things I want to test next.
Right, there's so many, and
because if I gotta send Bob stuff up anyways, and ship it all the way out there, I might as well include some samples of different metals as well, because that's stuff that he hasn't looked at yet, and it could be kind of exciting for him to get that in the SEM and figure out what the heck is happening there. Just to know that the same process was used on two different things, it would give us a heck of a lot more data than we have right now.
I fully agree and look forward to seeing what you come up with and the results. And here's another Walter Russell periodic table diagram that is vortex based, that is not so well known. Very fascinating stuff. Oh, you're muted, Jeremiah, if you're trying to talk.
Yes, indeed. I was not trying to talk. I was just actually looking at that chart, that spiral chart. And I was wondering where aluminum and iron sit on that chart to see how he represents that.
Those were the noble gases, I believe. So, no, so there's iron down there. So yeah, they're just further out. Oh, see there, we got bismuth and iron and Isotope. Oh.
Yeah, so where's aluminum?
Is it? I think it's on this side potentially, or no?
Oh, I think there it is. I think aluminum is like the thing that's covered up by tritium.
Yeah, aluminum right there.
Okay,
I
so
think so.
let's scroll back
And
down
then
to
it's on
iron
the
again. Let me see where
opposite
that.
side. Iron right here.
Interesting. Yeah, it's not directly across, but I don't know why aluminum is stopping at iron, or why it tends to prefer that. Not a clue. That's probably a question more for
Right?
Bob.
Or still to be discovered and answered.
Indeed.
And I
Well,
just, I
plus, and then
love how
the other question that people were asking too, which I should probably at least address, is in my experiment, how do I know that it's iron and not just some isotope of aluminum that happens to both change the color to being identical to that of iron, but also, could aluminum become somehow ferromagnetic if a certain number of neutrons were removed or added? The thing is, I actually don't know. I have no idea if some of the isotopes of aluminum are magnetic or not. I suppose it's possible that it could warp the shape of the electron shell enough to do that. Not really certain though.
So here's another periodic table that he has in the arch octave breakdown. Oops.
Yeah, I've just got to get a copy of all of these.
Right?
I might
know,
even
there's
have
so
them on my
much
computer
to
somewhere.
it.
I should
Tonal
probably jump
mates
off
of
though, man.
maximum stability. Yes, we are getting to that time of around 2 hours as it is, because I need to end it so AI can generate a bunch of clips out of this.
Well, namely though, it's also that 3 o'clock is about to roll around, and I need to go step outside and howl at the moon. And
no
I
doubt.
was telling people earlier, as the Earth, Earth's shadow covers the moon, we're losing all the blues and the greens and everything else that's of the violets that are of the higher wavelengths being pushed off at other angles, right? So all you're seeing is the reds, and I was saying just stare up at the moon tonight and imagine that it's just washing all your blues away. So because that's
I
kind
like
of
that.
photonically exactly what's happening. So I'm gonna go outside at 3 a.m. and howl at the moon. And
I'm going to
just
do the
release
same.
my worries.
Great advice, brother. Great science updates. Thank you for joining, and thank you everyone for watching. And we'll be back again soon. Happy Wormwood Moon to all of you, and go wash the blues away with the blood moon. Ta-ta.
Laser.
You crazy mother. Yeah.
It's just BurnEye. BurnEye just like last week, huh?
Weekend at Bernie's.